Hey everyone, hope you're all doing great. In this video, I'm going to talk about two very popular open source packages for incrementality testing. And guess what? They come from the biggies in the world of advertising and ad tech, Google and Meta, respectively. So the first one is Google's Causal Impact, and the second one is Meta's GeoLift. Now, they use very different methodologies, but the ultimate objective is very similar. So if you have any kind of intervention, and by intervention I mean suppose a marketing campaign, or you're trying something on a new channel and you want to understand the incremental impact of these interventions, you can carry out incrementality tests using these packages. Now the way they exist is very raw code, like bare code, so you have to kind of implement them through tools. Although Causal Impact has now got a ready-made version of it called Cosmos, so you have to run that through Google's um, Google Cloud. But yeah, this is a good place to get started. There are a lot of talks around incrementality now, so I'm going to try and dispel some misconceptions and also try to clarify what exactly incrementality test is and how you can start using these models and basically get started with it. So first of all, what is incrementality? Incrementality testing in marketing is the process of measuring the true causal impact of a campaign, right, or channel, as I was just saying. So it's basically trying to answer that question of causality. So whether or not something is causing another thing, this is generally difficult to answer through a regular correlation based approach. So a correlation approach is where you try to see the movement of two values, and you try to see if they're peaking at the same time, or they're sort of having a dip at the same time, and you try to figure out, okay, maybe these two are moving together, so therefore they're correlated. But that does not really mean causation. Something else may be confounding the relationship between these variables. That's where the importance of causal analysis comes into the picture, and that's the crux of what incrementality analysis really is all about. So how does it work? Like, you basically compare how much of the observed outcome can be attributed directly to the campaign or channel beyond what would have happened anyways. That's the concept of the counterfactual, meaning that you also have to somehow conceptualize what would have happened without the intervention. Now we will never know that for real for real in absolute in real life, because we don't know what would have happened if something that has actually happened did not happen, right? So that's kind of counterintuitive, but that's something that mathematics provides, and that's exactly what incrementality testing is going to do. So basically, the equation in a very simple sense, in a very linear way, is the conversions that came out of the test minus the conversions that were in the control. So you will have a control where you're not having essentially the incremental the intervention rather, and then the difference between the two will give you the incrementality. So that's your basic definition of incrementality. I'll just move on to something now which is also going on. Discussions around that is sort of going on a lot, and that's in-app incremental attribution. So Meta has come up with a new attribution model apart from its different standard attribution models like 7-day click and 7-day click, 1-day view, and all of that. So it's called incremental attribution. It's like I don't know, like a month old now or something like that. Now I'll basically argue, and I've already been arguing for a while now, that it's probably not the best way to go about incrementality testing. You would need a robust system, a robust framework, and probably third party tools or vendors that you can use, or you can use open source packages like the one I'm discussing, or if you really understand the math well, you can come up with your own systems. But the point is, this is probably not the best way, and I've jotted down three reasons. There could be more reasons. People might object to some of them. I'm happy to have those conversations. Great to have those meaningful debates. So first of all, it's a black box. The exact mathematical and methodological premises are very murky, so we don't know what's really going on behind the scenes. We can't really go under the hood and see what's going on. So that's the first problem. Directly contrasts with open source. As you can understand, open source gives you everything, the entire code base, everything that's going on behind the scenes. You can see, you can implement, you can play around with them. uh, if you think that there's any inherent bias, you can probably also change a few things. There isn't actually any such biases, but you can't say for sure if this one, for instance, which is in-app, like why wouldn't Meta, for instance, want to show its own platform's performance in a better light? right? Why would it want to give more attribution, say, to Google? uh, Obviously that's not really the objective of it, but I'm just saying, okay, so just to give some food for thought. Secondly, all this while we had a major issue with the platforms like Meta over reporting, taking credit for pretty much everything, right? This has happened for so many. Of course, the other side is also true for some cases where the view through conversion probably would have mattered more, and due to lag conversions, or because the attribution model that was chosen was more click oriented, that Meta did not get the credit that it should have got. But in many cases this is also true, like it basically over reports. So how are we and why are we to trust this black boxes suddenly? So that's also a question. And the third reason would be that in-app incremental attribution so far is basically showing lower numbers, and people are overall number of sales or conversions basically than standard attribution. And people, the marketers, they are some absolutely elated. They think that, okay, for the first time we have a very scientific method, and we are getting lesser numbers, so definitely this must be incremental. The problem is this reasoning is completely wrong. It's not how incrementality is supposed to be measured. You're not proving anything at all of that sort. You're just seeing a different approach, maybe, of collecting the data. We don't know what that method is, and as long as we don't know, we can't say anything about incrementality. See, the thing about statistical analysis is that it really needs to go through rigorous mathematics and equations and stuff like that. So there's a lot of theory, and you can't bypass that theory and say that, okay, this is what I think that is. And so you have to establish things. So it's a terribly misleading approach, and therefore I would suggest that you do not fall for this trap. I will move on to the next bit now, which is really the core, you know, topic of our discussion today, which is which is basically the two models that I was talking about: causal impact by Google and GeoLift by Meta. Now, causal impact by Google is it started out as an R package, and for a long while it was like that. Now it has actually been made available in Python too, which is great, and it comes from the Google research team. By the way, it's different from the Google's core ads team, and this uses something called a Bayesian Structural Time Series approach. So I'm just going to come to that in a moment. And the objective of it is to estimate the causal effect of an intervention, right? And it does so by doing the exact thing that I discussed while discussing the definition of incrementality, by constructing a counterfactual time series. What would have happened if the intervention never occurred, essentially? So you subtract that with the actual outcome from the, or you deduct the counterfactual from the actual outcome, and that difference gives you, that residual gives you the causal impact. So that is the simple logic behind it. Now I'll show you the code base. Of course, I've got a sort of a case study available to show, but I'm going to show you how actually this is working here. So if I just were to jump into the next one, which is GeoLift Meta. So GeoLift is an open source R toolkit from Meta's marketing science team for measuring geo-level campaign lift using synthetic controls. It supports data-driven selection of test and control geographies, power calculations, inference, and visualization. So you can understand this is a different approach. This now uses something in the space of geo holdouts, but without actually doing geo holdouts. So it uses synthetic controls. So geo holdouts is nothing but controls, geos or geographies which have been used as controls. Instead of having actual controls or holdouts, you basically have synthetic controls. Synthetic, it means that you come up with a set of geos which which have been synthetically selected using mathematical approach. This approach is called synthetic control methods. Okay, and you compare them now with the actual geos where the test will be run, and you see whether or not there's a lift. So this entire geo holdout has been synthetically reproduced rather than doing an actual geo holdout test. Now I'll just come to the mathematics of it quickly, how it's happening under the hood. So this is for Google's causal impact. Like I said, this is Bayesian structural time series, and it's basically what is called a state space model with latent components. Okay, now I know that's a mouthful, but I'll just try to break it down quickly. So you have an observation equation, you have a state equation, and the first one is observation equation, and you'll see that there are a couple of parameters here. So Z, and then there is alpha. So Z basically is your set of outputs, and that is going to be used for getting your YT. And you also have epsilon here. So I'm just trying to simplify it for you. And the alpha here, as you can see, has been defined by the second one. So that's your state equation. So these are the things that are changing over time. And you also have a ZT here. So if I just look at the definitions here, so Z, as I said, is it just picks out, it's an output from how the different hidden states contribute to YT. So that's basically your ZT. That itself is a vector. Your alpha T here is a latent hidden state at time T. And this includes different kinds of, so hidden state is nothing but different kinds of factors like say seasonality or trend, because it's a time series analysis, remember. So it can be always decomposed into say seasonality, trend, and residuals. So then you also have YT, which like I said is the observed value, and that depends on ZT, a combination of ZT and the latent hidden state, which itself then actually depends on this particular equation, which depends on a matrix that defines how the states evolve over time. So these things itself, the trends and seasonalities, they themselves have been taken as things which evolve over time, so they have not been taken as time independent. And then your R here, there's another coefficient which is a matrix, again a matrix itself, which defines how random noise affects the state. So that's your coefficient which explains the effect of noise on how the hidden state actually affects the ultimate observed value. So you have a number of factors here, as you can see, and it's a complex equation. This is a system of two equations which ultimately defines the entire structure of BSTS. So it's a Bayesian system. It uses the concepts of likelihood and prior, and based on that, it sort of tries to understand how this time series model actually should be looking like, and how the output is going to look like. So just to describe these two equations again, this tells you the first one, the observation equation, how the observed data is produced. It's a combination of hidden states mapped through a weight vector plus some random noise. Okay, so it's a combination of hidden states and some random noise. And the second equation is the state equation. So by the way, the observed value is therefore a weighted sum of hidden factors plus noise. That's how you read this equation. And the state equation is simply the explanation of how the hidden state vector changes over time. So like I was saying, like the different components of time series, like seasonality and your trend, all of that is also going to change over time. So it's a combination of these states, and these are hidden because you don't really know, and that's why these are latent terms. So that's why it's called latent components. And what the states were in the previous time step plus a shock or noise term is what gives you the state equation. Now, I know that's a mouthful, but this is sort of to get you started. If you are technical, or if you are looking to try and code this, or try to understand how this works, you should give this a go. Now, I'll come to synthetic control methods. And in synthetic control methods, you'll see that there's a weighted combination of control units, and there's matching pre-treatment characteristics. There are two important equations, again a system of equations. Lot seems to be going on here, but it's actually relatively simpler than BSTS. It's simply a weighted combination of control units. Just think of it. These weights, this W here are the weights, and WJT are the different outputs, are the different observed values from the different control units. So based on that, you're trying to understand a predicted value. Okay, so you're trying to observe. So if I just go to this equation here, this estimates the counterfactual outcome. So this outcome is what would have happened without the treatment for the treated unit. Okay, so this is a weighted average of the outcomes, the actual observed outcomes of untreated control units, and the weights are assigned to each, the W's. And these weights are chosen to construct a synthetic control group that closely resembles the treated unit before the treatment. So that's the whole point. Like, you have a control group and you have a test unit, and you want to, by the way, your test unit is usually one in case of synthetic controls, but you can have augmented versions of it where you can have multiple test units as well. So this is the counterfactual outcome. So you want to understand how well, or you want to basically choose synthetic controls which resemble very closely the test unit. And how do you do that? You do that basically by equating the counterfactual or sort of conceptualizing the synthetic controls as a set of units which would have behaved in a very similar manner to the test unit had the test unit never undergone that intervention at all. So I know this sounds a little complex, but this is basically the crux of the idea. So that there is a lot of conceptual elements going on. Then the next equation is simply about matching the pre-treatment characteristics. So you have this difference here within the summation, as you can see, and this simply gives you the difference between the value of the covariate h for the treated unit and the value of the covariate h for the control unit j. So you basically have the differences between the treated and the control unit that gives you the actual post-treatment effect. So obviously you still have the weights, you have the relative importance of the weight and all of that in this particular equation, right? So these are the two equations which are the guiding forces behind synthetic control methods. I strongly urge you to try and take some time to understand these. Now I'll quickly walk you through the actual code itself as well. And so if I just jump into the code here, this is for causal impact analysis. And what has been done here is there was this is based on an actual experiment. There was some change that was done on the website, and basically an effort was being there was an analysis done in order to understand what the actual impact of that change in the website was, whether or not there was a change in different things like say new customers and new customer revenue and total revenue and everything pretty much, even conversion rate. So this is, for instance, the total revenue plot that was done, and you'll see that this is a pre-intervention and post-intervention which have been clearly demarcated, and you'll see that there was a significant increase in the post-intervention period. Okay, or that's what it would seem like, although there is an up, there's a rising trend here as well. So that's what this will do. So try and understand what we just discussed, and try and recall what we just discussed in the theory about BSTS. That BSTS will try to recall, not recall, rather extract from the information from the data that is already available regarding the underlying factors, the latent factors. So if you have say trends, if you have seasonalities, it's going to try and extract all of that for you. It's going to do that hard bit for you. Okay, and then it's going to try and predict the counterfactual on the treated unit had there not been an intervention. So now I sort of invoke the causal impact package, and there it gives me the actual impact plots. So this is your actual versus predicted, as you can see, and this gives me basically how, the black line shows how the actual observations were, and then the prediction is your blue line. The shaded part here for the blue, that's basically your confidence interval. So that's how much the variation would have been as per the expectation. The point effects basically give you the difference between the actual and the predicted and how that has evolved over time. So you can see that there is, the difference has been varying quite a bit. Um, I don't know how much causal impact was there in this case. Again, it depends. I mean, it does not necessarily mean that an intervention is causally significant, right? Or causal in nature. And that's precisely why you're doing this kind of a test, right? That's exactly what incrementality test is going to try and establish. So this is your cumulative effect. This is basically, as per the definition of cumulative, over time how much the effect is getting accumulated. So that's your primary output. Then you also have an output that so you also have a textual output, by the way, which sort of gives you whether or not the causal impact has, whether or not it has been properly causal. Let me just see. So so there you go. This is the prediction. So you'll see that there's a posterior probability. It's zero point 0.3. So basically it's not significant. Statistical significance means that it has to be less than 0.05, right? So there you go. That just kind of shows you that it's actually not statistically significant. And to understand whether or not this test was actually done in a reliable manner, you also have standardized residuals, the distribution of the residuals over time. And the residuals are the difference between actual and predicted. So plotting them or visualizing them and understanding their distribution is actually very important. And this is a histogram, and it's also a KD plot together with it, which gives you the line plot for the residuals. You can see that they're more or less normally distributed. and they are also kind of fairly random. And the normal QQ plot is also just saying the same thing. If it lies, if all the points lie on this normal QQ plot, the theoretical quantiles line, basically that means that it's normally distributed, the residual distribution. And whether or not there's any autocorrelation is given by, or any autoregression is given by, or ACF plot. Okay, so that's also called a correlogram. And you also see that there's not much here, so there's just really white noise, which is only useful for the, you know so as you can see, which is only useful for the model. So it appears more or less normal, which means that the normality assumption, which is a very important assumption for regression based models like this, it's actually fairly decent. Now I'll quickly jump into the R Studio. So the R Studio is actually where I've run the GeoLift model. Now they have a Python version, but it's actually quite a pain to actually run that on in Python. So I've tried using the R Studio version of it, and essentially this is where the entire code has been run. So in the R Studio, and in fact, what I'll do is I'll jump to the actual notebook on the website itself, because R Studio is a software and kind of you know makes your system slower sometimes. So I'm just going to stick to this, and you have a lot of documentation here on GeoLift. I encourage you to try and go through all of that. But you also have the installation, first of all. So you have to install in RStudio, the packages like Oxynth and GeoLift. And then you can basically have all the libraries like ggplot, which is going to give you the visualization. So the idea about GeoLift, remember, is to carry out a geo experiment, right? And your geo experiment is going to tell you whether or not, between the holdouts and the test geos, is there any causal difference, or the intervention is causing any, is causally significant. So basically what it does is, the first step is to run a GeoLift test, and you basically load a geo pre-test data. So that's where the data has been predefined by the system. Here you provide the date ID, which gives you the column for the date, and then you have the locations of the geos, and basically the YID is your. So these are values basically that you have to provide to the system, and then you can identify the right columns for the analysis. So the head gives you the first few rows here. So this is in R, by the way, like I said. So again, I honestly am much more familiar and comfortable with Python, but I kind of had to run all of this within R Studio. So all of this is actually here only, but I'm just reading you through the actual document, just so that it doesn't cook my system. So the geoplot, geotest, pretest, and this basically does the geoplot over the pretest data, and you can see how the data looks for the different regions. Okay, and this basically gives you Y. So that's basically your sales data. You can take Y as a sales, as a sales variable, and you can see how this has actually varied for some of these regions. It's actually quite on the higher side, some of them on the lower side. And this gives us a pattern, and you'll see that these are shared structural similarities between the different regions, and this is actually important. So over time they actually vary in a very similar fashion. So this is one of the requirements of the GeoLift test. And if the geos are very different in characteristics, how they're varying over time, they are not peaking at some sort of similar times, it means that there's a lot of difference between among the geographies, and you can't really do a very proper GeoLift test, because the whole idea of it is to choose a set of geos that will be very similar, for the sort of set of geos for controls, which will be very similar to your test geos, or test geo. But that actually depends, that your data will be suggesting as well, how different is the, or how similar is the distribution. The next part is the power analysis. Now this is the most important part of the GeoLift test in the pre-test phase, where you're trying to understand how statistically significant is going to be a certain lift. So suppose you're trying to look for a lift of say 5% or 10% or whatever, that's your MDE, minimum detectable effect. How much explainability is going to be there? Like statistical power is kind of in a very simplified fashion, is going to tell you whether or not that's a very, you can give a very confident estimate of that. You can confidently state whether or not that's the case, whether or not there's a causal impact. This is not the real definition. I'm just giving you a simpler version of it just so that you can understand it better. So if I just jump down to this point now, this is where the market selections, the GeoLift market selection is taking place. This is where it's actually taking into account all the different geos. It's taking into account the treatment periods, okay, and it's creating an effect size. So it's creating a synthetic effect size here, which means that that's basically how much the effect of the intervention is happening in different regions. And there's also sometimes a predefined requirement for inclusion and exclusion of certain markets, so that has also been defined. So there are a lot of values here. There's a total budget that's been pegged at a certain value. There's the CPIC, which is the cost per incremental conversions, and you have finally this kind of an output. So after running that geomarket selection, you basically have these outputs here. So you have these outputs here, which is effect size, which is represents MDE, basically the minimum lift needed. And you can see that this has been kept in this fashion. It's a sequence ranging from 0 to 0.25, which in steps of 0.01. And then you have say power, location, duration, ID, which are very simple. This is a new thing. So average scale L2 imbalance is an important factor, which it's a measure of goodness fit essentially, which is 0, which varies between 0 and 1. how well the model is how well the model is suitable for predicting the pre-treatment observed values through the synthetic control. So that's basically what it's trying to do. It's trying to give you that match between the geos in the control and the test. So you have your average ATT, how much is the average value of incremental effect. The total proportion of Y is the fraction of conversions that happen in test regions compared to the conversions in all the regions. Absolute lift in 0, it represents whether or not the lift is really taking place because of the intervention, or it would have happened anyway. So it should be close to 0. Then there's holdout, what percentage are in the holdouts, what percentage of geos. And then you have a ranking system based on these different values, how high ranked is the geo, or as in terms of being suitable for being chosen as a synthetic control geo. So you have the observations per timestamp and different geos and test group. So this is how they're faring, and you'll see that there's a very close similarity between the treatment and the control. And this is basically for market ID 1. So you have chosen Chicago, Cincinnati, Houston, and Portland for a 15-day test. And you can see, and so from the outcome, basically from this outcome here, this was basically found out, okay. And now you separately plot it out just to confirm it, and you see that the geolift curve here that actually shows you that the for the treatment periods, what is the effect size for different power values. So like I said, 80%, you'll see that there's a dotted line here at around 80%. That's your chosen statistical power. Usually that's a universal standard. And you'll see that the effect size is somewhere around 5 to 7% at a statistical power of 80%, roughly 80%. So that's what you will typically get. That's what you can expect basically after the analysis. So you can't expect, suppose, 25%, because the curve doesn't show that being as possible at 80% statistical power. So that's basically a very nice way of looking at statistical power, and this gives you the pre-test analysis. There are other ways to do multiple iterations. I'm not going into that, but ultimately it gives you the same thing. For every iteration that you do, try to understand whether or not the synthetic controls are a good choice. The geos chosen are a good choice for being in synthetic controls because they match the characteristics of the pre-test of the test regions. That's basically given by this power analysis part. Then you also have the analysis of the test results. This is where you upload another test data. They obviously have a synthetic data. That's what they're running here. Again, 40 locations. You'll see that this number remains constant. which is important, and then you see the first few rows, and then you again plot them over time, and you have this dotted line that actually gives you that intervention period. So these are the different geos and how the sales varies over time, and this dotted line actually tells you the intervention period. So you'll see that this is the post-test data, and now the GeoLift inference has to be done. So that's where you invoke the GeoLift method, and then you invoke it using the GeoTest data. You give the locations as Chicago and Portland. The treatment start time is 91. There you go, and you'll see that the end time is 105. So between them, how much is the effect? And you will try to get the GeoLift output after that by simply invoking or calling GeoLift, and it shows that it has a 5.4% lift, and incremental absolute value in sales is around 4,600. Estimated treatment effect is 155, and you will also see that the results are significant at 95% level. So that's your average estimated treatment effect, by the way, and the results are significant at 95% confidence interval. So there's a 1.4% chance of observing an effect this larger, or this large or larger, assuming treatment effect is zero. So this was supposed to be as close to zero as possible, and you can see that it's very small percent, right? Because this is basically your absolute lift in zero. So this is it. I mean, you also have obviously other plots like observations per time step and test group. Again, this is basically actual versus predicted, and you see that it's pretty decent, right? There's this confidence interval that is shaded, and this is your average treatment effect, and you can clearly see the average effect on the treated. This has increased during this phase here. The effect has increased. Okay, so the magnitude of the effect on a daily basis in contrast with the lift which plots on aggregated effects. This was aggregated, this is on average, and you'll see that it has very small ATT values in the pre-treatment period, and the large ones when the treatment has been administered to our test locations. So that's your point. Like, the treatment should not, it should not be like you ran a campaign and you see that the average ATT is also pretty high in the pre-treatment period, which means that it's not conclusive, right? But there's a clear difference between the pre and the post-test periods. So it's it's relatively complex to execute. That's the beauty of these models and the systems, how incrementality tests really work, and these open source models really work. So conceptually speaking, BSTS is more difficult, the mathematics of it is more difficult, but to execute the way causal impact, and that's a thing with a lot of these Bayesian systems, that they're not very complicated to execute. It's much easier to actually execute. Remember, I showed just a very limited lines of code, of Python code that were required to execute the causal impact model. But for the GeoLift, it was far more, right? And that's typically the nature of frequentist kind of approaches, or whether you call it Bayesian or frequentist is immaterial. The point is, at the end of the day, what the method is and whether it works or not. But I just wanted to sort of divert your attention once, or sort of channel your attention towards this point, that BSTS is a more complex method, but because of the way the causal impact package has been structured, it's relatively easier to execute. GeoLift is a simpler concept, it's based on synthetic control methods, but its execution is more difficult just because of the nature of the code itself. It's pretty extensive, and like I said, I ran it in RStudio. They actually don't have a proper Python code for it. It's not a native code. It's basically going to use R code, but you're going to use something called a Python wrapper. So you have to invoke R within Python environment, and that kind of is fine, but it can get tricky sometimes, and it can slow down the system. It is fairly resource intensive. You basically have to choose a different kind of um, system. So you have to choose a different kind of runtime type. So the different kinds of runtime types are there. So for instance, this was running on CPU, you'll probably have to go for an LPU or GPU, a GPU or a TPU rather, in order to run that properly. If you have to run R within the Python environment, like say Google Colab. So this was the analysis that I wanted to share with you. This is as you can understand, a no bullshit and no nonsense kind of an approach that I've taken. I tried to talk about all the technicalities. It's a highly technical system. It's a highly technical domain. It's not something that's you know uh, that you can just pick up overnight and can just run a few prompts on chat gpt and you can come up with this. This requires a thoughtful deep understanding and a thoughtful analysis. People need to spend time on it, and people who have the knowledge of these systems and the mathematics and the code behind it. So it's best to I'm not saying that no one can learn this. Anyone can theoretically, but the point is that if you have a lot on your hand already, suppose you're a performance marketer, you would rather probably just take the help of measurement experts. Again, I'm saying that it could be vendors or it could be individual experts, but the point is, do take help if necessary. Don't just leave it till late and sort of rely only on half-baked advice from people who actually don't know, or from sources which are not very reliable. So anyway, I just wanted to dispel all of that misconception and try to show you the most scientific method. Hope this was useful. If you have any questions, do let me know in the comments. And as always, thanks a lot for watching, and I'll see you in the next one.